Okay, thank you. So I was asked to speak about, by your chairman, who I believe is not here, about how I predicted explained the maximum luminosity of galaxies. And when I thought about this and went back and read some very old papers from the 1970s, I thought this isn't true, I haven't done this, and so on and so forth. So what I'm going to do is tell the story of how we have come to understand how we understand galaxies are formed, which I think is knowledge we've gained entirely since I was a graduate student in 1972. And my thesis was entitled On the Formation of Galaxies. So while I have not done most of this work that I'm going to talk about, I did think about it back then. And, oops, no, I'm supposed to be using this. Oh, it was working before. Choose, click on the win. Maybe I should just have that. Oh, right. Yes, I see. Okay. So, all right. So here is my outline. I'm going to talk about the problem as it seemed in 1972, why it was a good thing to be thinking about then, and about the physics that might set.
Boy, I love you. Be well.
And then I will talk about the theory that developed then, that was nascent then, but has developed much since, about cosmic fluctuations, Gaussian random fields, and then talk about simulations of galaxy clustering, and the crucial question, which have been very successful in the area of dark matter, but how to go beyond dark matter, why you have to go beyond dark matter in order to explain galaxies, why there is very powerful feedback, what you learn from clusters and groups of galaxies, and all that tells you basically explains why there is an upper limit on the effectively on the mass of galaxies. So back in 1972, when I became a graduate student, the situation was that the Big Bang had killed off, well, discovery by Penzias and Wolfson with this remarkable antenna in the corner there in New Jersey, had killed off the steady state theory, which my supervisor, Dennis Sharma, had been an energetic proponent of, killed off this theory and established beyond reasonable doubt that the universe did indeed start with a Big Bang, which is surely one of the most amazing propositions ever established by scientists. Now, the thing about and Hermann Bondi had explained how you should think about relativistic cosmology, how you can think about it in a largely Newtonian way, get a real intuitive feel for what's happening in the ideal universe, in the perfectly uniform, isotropic, homogeneous universe. Any point can be taken to be the center of the universe, and then matter recedes from that center with a velocity v that is some constant, well, called a constant, there is some number h, which is a function of time, times the distance r of the point that's receding. And in the original undisturbed universe, before you think about any fluctuations, there's evidence that the kinetic energy in each of material is always equal to its potential energy. So in other words, all particles have zero energy. That means that they can escape to infinity. But when they get to infinity, they will have everything invested in P and have no KE left. In other words, the expansion of the universe is going to continue forever, but go on slowing and slowing and slowing, so that asymptotically every particle comes to rest at infinity. A very remarkable state of affairs, which people invented the idea that the proposition that somehow the kinetic energy is precisely which was enormous, was precisely equal to the potential energy, which was enormous, because the universe was so very dense. The theory of inflation, which I think is wall-to-wall bunkum, claims to explain that. Okay, then given this perfect balance between kinetic and potential energy, if you have the tiniest overdensity, or indeed the tiniest slowing of the expansion, which will soon lead to an overdensity, then matter in that volume has got slightly less kinetic energy than it has potential energy, and so its expansion will come to halt at a finite radius, after which it will fall back towards the positive center of your sphere. And back then, it was a question that people asked themselves. Maybe elliptical galaxies or maybe globular clusters formed precisely in this way at rather high redshift, when the density of the density of the universe was still very large. So at a redshift of more than 30, at 30 say, the density is 30 cubed, so 30,000 times larger than the density now. So maybe at this kind of era, some of these things came to rest and fell back. But so that was a potential explanation for formation of elliptical galaxies or globular clusters, but it didn't address questions like where does the angular momentum associated with the sun, because the sun is on an orbit nearly 10 kiloparsecs, 8.3 kiloparsecs from the center of our galaxy, moving at 250 kilometers a second. Where does this angular momentum come from? How does it? How does it happen that there's all this gas in spiral galaxies from which stars like the sun formed long after the early phase of the universe, and so on? And to try and address these questions, people thought about what role does atomic physics play in all this? Does atomic physics set cosmic scales? So when you count the number of galaxies, dn by dl, the number of galaxies per unit luminosity, per luminosity interval, Paul Schechter back at this era showed that this could be very well, the actual number of galaxies could be fitted very well with what's come to be known as the Schechter luminosity function, which is to say that the n by the L is looking like L over some characteristic luminosity L star to the minus alpha, where alpha is a number like 0.7. It's an empirically determined number, so there's a bit of uncertainty about it. So it's a power law which predicts that there are more and more low luminosity galaxies, but it doesn't continue to arbitrarily high luminosities. It's exponentially cut off at this luminosity L star. So that there is a characteristic luminosity of galaxies, L star, even though the overwhelming majority of galaxies have less luminosity than L star. This characteristic luminosity is very important, because if you ask where most of the stars in the universe live, that's associated with the function L times dl by dn by dl, which is a function which peaks around L star. And indeed, the Milky Way has a luminosity which is very close to L star, and it's presumably not an accident that our galaxy has a luminosity close to L star, because if you simply ask the question, if you choose an appropriate star for Homo sapiens at random from all the stars in the universe, what's the luminosity of the galaxy going to be? The answer will be on the order of L star. That's the most probable place. That's where you're most likely to find yourself. And presumably there are indeed civilizations all over the universe, some of whom are in small galaxies, much less luminosity than L star, but they're few compared to the many of us who live in L star galaxies. Okay, so one of the things you want to know is, where does this L star number come from? What is it in physics that's L star? So these galaxies, L star galaxies, have characteristic length scales which are on the order of a few kiloparsecs. We live 8.3 kiloparsecs from the center of the sun in a disk which has an exponential density profile with a characteristic length of about 3 kiloparsecs and velocities of a couple of 100 kilometers a second. Now, atomic physics does contribute characteristic energies, of course, on the order of an EV, etc. And they translate into characteristic temperatures through KT is equal to these characteristic energies, and therefore, of course, velocities on the principle that a half mv squared, when m is the mass of a proton or whatever, is on the order of KT. So the cooling curve of pure hydrogen, oops, oh dear, I've done the wrong thing, hit the wrong button. The cooling curve, oops, here we go. The cooling curve of just a hydrogen-helium mixture, which is what there would have been in the universe before the stars formed, looks like this. Is a logarithmic scale. So there's a factor of 100 between here and here. So this is the cooling rate per atom as a function of temperature, 10 to the 4 Kelvin, 10 to the 5 Kelvin, 10 to the 6 Kelvin. And the point is that between 10 to the 5 Kelvin and some by 2 by 10 to the 6 Kelvin, there's a temperature range where the cooling rate falls very steeply as the temperature rises. Now that's a very exceptional thing. Any cup of coffee or whatever, of course, cools faster as its temperature rises. The reason you have this fall here is because in this temperature interval, atoms are becoming more and more ionized, and nearly all the radiation from a plasma, that contains any bound electrons comes from the bound electrons. And once you get rid of the bound electrons by heating the plasma above the ionization energy, well, you don't have to heat it that hot if the density is very low. But once you get them ionized, the radiation efficiency of the plasma becomes very low. Now, the consequence of this is that you expect a two-temperature regime. You expect to find material down here at about 10 to the 4 K, because this is a regime where the radiation increases as you heat the plasma. So it's kind of stable. You heat the plasma by a certain amount. If you heat it a little bit more, you just raise the temperature a little bit more, then that raise in temperature increases the radiative capacity of the plasma, and so it returns to equilibrium with your increased heating rate. But once you get it over well, indeed, even here, once you get it over one of these places where it starts to fall, if there's an upward fluctuation, I mean, if we heat it so strongly, we get it up here. If the temperature fluctuates upwards at all, then the radiation density effectiveness decreases, and then the heat we're putting in is way too much for what can be radiated, and so we go more and more out of equilibrium, and the temperature rises and rises and rises and rises and rises, and slowly settle over here somewhere, where the heating rate would have to be here. So we expect that there's that there's a hot phase and there is a cool phase. The cool phase is associated with temperatures less than about 10 to the 4 Kelvin, and the hot phase temperatures bigger than a couple of million degrees. And that means that there's a characteristic that introduces a characteristic velocity, which is indeed on the order of a couple of 100 kilometers a second, coming from this couple of million degrees, right? Because, as I've said, the hot plasma has a sound speed which is on the order of half mv squared is equal to kT, and we have characteristic temperature a couple of million degrees or whatever. And if through this formula you ask, well, what's the characteristic speed of the atoms? Answer, it's a couple of 100 kilometers a second. And there's another scale introduced by complexities that are really not properly understood, of supernovae. So supernovae, which come in two completely different classes. There are core collapse supernovae, where a massive star that starts out in life with a mass bigger than about 8 solar masses, develops a core which general relativity makes unstable, and it collapses to a neutron star or a black hole at the end of its life, and that ejects material at maybe about 10,000. That by processes that are not properly understood, but to do with an enormous burst of neutrino production as the baryons pile together in this relativistic object, the collapsed core of the star blasts the envelope of the star out at maybe 10,000 kilometers a second. And then there's the other type of supernova, which is when a carbon and oxygen white dwarf accretes too much material, and nuclear reactions start in an unstable way in its degenerate core, converting the carbon and oxygen overwhelmingly into nickel and iron in only less than a second, and that then spews stuff out at maybe 5,000 kilometers a second. So out of supernovae, you get, so when this fleeing material bangs into the surrounding insular medium, you get a shock, and the shock heats material to about 10 million degrees Kelvin, and that then provides another characteristic temperature and therefore a characteristic velocity in the system. So there's right from this early period, there was a feeling that the scale, the characteristic scale of galaxies was probably set by these bits of atomic physics. So it's clear that it was already clear that from the game was that there would be fluctuations in the density and the expansion rate in the early universe. These fluctuations were originally very small, but they grew through gravity amplified them until eventually some block of the universe ceased expanding, collapsed, and so on and so forth. Now, Doroshkevich, there was a very strong Soviet and quite distinctive community of scientists at this time, and it was important to read the Soviet literature. Yavin Zeldovich was an amazing scientist. He worked in a huge range of fields and was probably the most important person in the Soviet hydrogen bomb program in the early 50s. But from about 1962, he devoted himself to astrophysics, and you had to go to Russia to see him because his head had contained various nuclear secrets, and so they wouldn't allow him out. But anyway, his student and he pointed out that the way you should think about the fluctuations in the early universe was as a random Gaussian field. So what that is you say the overdensity, so delta here is delta rho, the excess density, which might be negative, right? Positive or negative. So delta rho over rho, you should expand as a Fourier series where these amplitudes are complex numbers. The magnitude of this complex number, or magnitude squared, is given by some function p of k, known as the power spectrum, and the phases of these random numbers are the random part, but they go from 0 to 2 pi with equal probability. So a field made like this is called a Gaussian random field, and when you ask, so what then happens when at an early time you impose such fluctuations on the standard uniform expanding critical universe, you find that overdense regions tend to become highly non-spherical, in fact sheet-like. So you start with, this is a little schematic, right? So suppose that's a contour of overdensity at some early time, then at some much later time, this thing will have, which was just mildly elongated this way, will become highly elongated this way, and material that started up here will be banging into material in the middle plane, the equatorial plane of this object. There will be a shock formed by material that started on the top, banging into material that started on the bottom. And in that shock, material might be heated. So in my thesis, I worked on the consequences of this kind of thing. But I won't bore you, I think, with too much details about that. So the thing is that this model is entirely determined by the function p of k, the power spectrum. So it's just a function of one variable, k, which is the modulus of the vectors k. And Zeldovich argued that the primordial power spectrum would be p is proportional to k. And there were two reasons for this. One is that the power spectrum should be simple. It shouldn't impose any scale. Scales should come from somewhere else, like atomic physics. And nothing is so simple as a power law. And if p is going to be on the order of k to the n, then n has to be 1, because if n was slightly bigger than 1, that means that the power would rise with rising k slightly faster than 1. So there'll be more power, in a certain sense, on small scales. And what you would find is that at the very smallest scales, the fluctuations would become relativistic. And that was inconsistent with the smoothness of the apparent smoothness of the universe. And if n was slightly less than 1, then there'd be a lot of power on large scales, and the universe wouldn't be homogeneous and isotropic on large scales as it was known to be. So just on this argument that there's a huge range in which which the universe at early times seems to be smooth, forces you to think that P is on the order of K. Now, the Buncombe theory of inflation claims to demonstrate that that n is 1. That's the more conventional interpretation. But this, since inflation is Buncombe, and I'll explain to people afterwards why it's Buncombe. This older, very simple argument of Zeldovich, I find much more convincing. Anyway, the spectrum. It has been measured subsequently, and P is very close to K, and is very close to 1. Okay, now this is the prime. Zeldovich was talking about the primordial spectrum, the spectrum, way back in the very first fireball. But as the universe evolves, as it expands, P of K evolves away from the simple power law form, because fluctuations grow so long as they have a bigger scale than the horizon. The horizon at any time is basically it's defined to be a block of the universe, which is how far a photon could have traveled in the age of the universe up to that time. And bits of the universe which are smaller than the horizon during the long radiation-dominated era behave like gas. The radiation provides pressure, which allows them to expand again if they're compressed. So fluctuate until the horizon is hit, until the horizon, which is always rising in size, gets to the scale of the fluctuation grows because pressure isn't able to fight back. But then once the fluctuation is inside the horizon has come and met it, the fluctuation is smaller than the piece of the universe which is supported by pressure, then the densities just oscillate like sound waves and don't grow. And then they grow again once the radiation decouples from the matter, which it did at a redshift of about 3000. So the basic point is that very long scale, small scale fluctuations aren't able to grow for very long because they're on small scales. The horizon reaches them very early, so they stop, and then they stop growing. Whereas large scale fluctuations go on growing, and as a consequence of this, the fluctuation spectrum now looks like this. So here, this is K. So large scale fluctuations at this end, small k, and here is the original k to the 1 thing. And then here is a much steeper fall off. So the primordial spectrum would have gone on up and up and up and up, but it's come down here because these fluctuations weren't able to grow. Were only able to grow for a short time because they have short length scales, and the horizon met them very soon. Whereas these ones grew for longer, etc., etc., etc. So, and there is excellent agreement between the data points and the theoretical prediction based on these sorts of ideas, which is the code. Okay, that's the power spectrum. Now, what we really want to know is what is the fluctuation in the mass inside a sphere of radius, of some radius. So now let's put the radius 2 pi over big K. Then the variance of the mass inside spheres. So you make spheres all over the universe, and in each sphere you will have a certain mass. You then compile the statistics. There'll be a variance of the masses because there are these fluctuations. And the question is, what is this variance in the mass? Well, it's given by this integral here. The key thing is that waves which have wave number bigger than the wave number associated with the radius of your spheres don't contribute to the overdensity, because those waves contribute both positive and negative. So they have both crests and troughs within your sphere, and the crests and the troughs cancel out. So the waves which are shorter than the characteristics of the thing of the sphere, so that you can have both crests and troughs within the sphere, don't contribute. So big spheres, which have small values of big K, enjoy this integral, or in this integral, P is contributing over a relatively narrow range of Ks. Whereas small spheres, which are associated with big Ks, have more, this integral goes on for further, and so sigma K is larger. So within small spheres, there are large fluctuations. Within big spheres, there are small fluctuations. And if you want to know what the curve looks like, at the end of the day, it looks like this. This is the variance in the mass. This is a measure. This is now not K, but the mass, the mean density inside the sphere. So this mean density is variance, and you can see that at small masses is a logarithmic scale, right? So this is 10 to the 5 solar masses. This is 10 to the 10 solar masses. Small ones, you have large variance, and large ones, you have a small variance. The consequence of that is that small spheres collapse first. Small spheres have large fluctuations in their density. And so at an early time, some of these fluctuations will have been enough to reverse the Hubble flow and cause a collapse. So small spheres collapse. Spaces, regions, voids, regions which are below average density, because actually in a Gaussian random field, the overdensities, the geometry of the overdensity is exactly the same as the geometry of the underdensities. If you were shown a contour map of a Gaussian random field, you wouldn't be able to tell from the shapes of the contours whether you were looking at mountains or lakes. But gravity stops it being a Gaussian random field, and this illustrates, slide illustrates it. So what's happened here is Dubinsky has put a lot of points down. This is a toy universe, right? So he's got a lot of masses which are receding from the center with the Hubble law, but he has slightly reduced the density in 3 regions here. And within each of those 3 regions, he's taken some even smaller regions and reduced 3 smaller regions and reduced density. It's clearer in this picture after it's evolved for some time. So think of this as a very small sphere, and this is the sphere after it's expanded, but then it's zoomed out so that it has the same it's the same size on a piece of paper. And what you can see is these voids. So these what were very small underdense regions have become very underdense regions, because in these small regions, underdense regions, there's not enough gravity to pull the particles back, so they expand. They travel out further and travel and kind of squeeze the overdense ridges between them. And you can see more squeezing here, and now these bigger overdensities are causing squeezing material between the ridges between them. So, and meanwhile, the little ones are rather fading. Now we have a network of overdense regions here and here and so on. Right. So the point is that is that the fluctuations generate, the gravitational amplification of the fluctuations generates a sort of web, a kind of network of overdense regions surrounding voids. Also, which is not so apparent in this slide, so what's going to happen here is that we're going to have stuff on here and here and here is going to fall in there, and we're going to have a galaxy forming there. So overdense regions turn around and collapse. underdense regions expand and become voids and squeeze material into sheets. And this is just a straightforward numerical simulation of that, starting with a random field. And I think you can see that you have a kind of network of overdense regions which increases in scale. Here, you have a bigger scale network. So, so you have a sort of foam which forms when the fluctuations cease to be linear. And this foam morphs over time into a bigger pattern, and then it morphs again into a yet bigger pattern. The scale is constantly increasing. The scale set by the ridges between the voids, and also the mass of the objects which collapse. You can't see that there's a collapsed object here, basically because there's burnout in the picture. The thing is either black or rather white. You can't see just how high the density becomes in one of these places, but it does become high. And this is an observational. This is a redshift survey, the 2-degree field redshift survey done in Australia. And I think you can. So this is showing the redshift now, which is more or less distance of the galaxies, which are dots. And I think you can see that there's this kind of network. So this is all in great shape. And you might think, oh yes, okay, so we've understood how galaxies form. But we absolutely haven't. And the reason is that we've been thinking, essentially, about matter as being just a dust of particles, which don't collide with each other, just interact gravitationally with each other. And the real visible universe is very much associated with atoms and things, with ordinary matter. So one manifestation is this, that if you count the number of halos, the number of collapsed structures as a function of their mass in a simulation like the one I was showing you there, you get this curve here. So there are more and more low mass objects, and this is more or less a power law, because this is a log plot. It's a straight, more or less a straight line. But this power law is truncated at the very highest masses, very much like the Sheckler luminosity function I showed you at the beginning. And this characteristic mass, which is here something a bit below 10 to the 15 solar masses, is constantly increasing as the universe ages. The structure, so this curve is morphing through the merging of halos, or even bigger halos, which cause this endpoint to move to the right. If you now ask, well, what does the luminosity function of the galaxies look like? Well, the answer, it looks like this. In order to put the luminosity function of the galaxies on the same plot as the number density of halos by mass, we have to assign a mass to each halo, and here the mass has been assigned to each halo by multiplying the luminosity by 200 solar masses by solar luminosity. But the point is, no matter how you do this, you can see that by shifting that scale, you could move this horizontally. But I think you can see that there's no way, no moving this horizontally is ever going to make a degree of this curve here. There are two problems. One is that this turn down occurs way sooner than this turn down in the full curve. The other problem is that the sort of power law resection here is flatter in the galaxies than in the dark matter. So, why is that? Well, if we were looking at dark matter, the universe wouldn't look like this at all. So this is the picture I had as a background on one of my first slides. It's the Hubble Deep Field. And the crucial point is that there's an awful lot of space between the galaxies. Actually, there's very much more space between the galaxies, and this picture gives you the impression because this is a picture, a photograph taken by looking through an enormous depth of the universe. So these galaxies, which appear to be close to each other, are probably not close to each other at all. They have a huge distance along parallel to the line of sight between them. So the key thing, a key fact about the real universe is that the galaxies are rather small, very much smaller than these dark matter halos. And why is that? That's because when the dark matter tumbled together, it conserved its energy because it's collisionless. So when it converted its potential energy into kinetic energy, that was it. When ordinary matter falls together, like I said, with the Zeldovich model or whatever, it bangs into other matter coming from another direction, heats to a high temperature, radiates, loses energy, and so collapses further. So the galaxies are very much smaller than the dark halos as a function, as a direct consequence of the radiative properties of ordinary matter. Now, I said as the cosmic web regenerates itself, increases its scale by this process of merging of halos and voids, the velocity scale increases. So what we have here is the characteristic velocity scale in purely in a dark matter kind of situation as a function of mass. And so as you go to higher masses, which characteristic velocity increases. And therefore the characteristic temperature scale associated with the objects of different mass increases. Now, when Z becomes so, and I think I said, I did say that as the universe ages, the characteristic mass, the turnover, this mass, at which the power law turns over to a more or less exponential cutoff, that increases. So at each redshift, there is a characteristic maximum mass, a mass in which most dark matter particles are tied up. And that mass is constantly increasing, and therefore the characteristic velocity associated with those dark matter halos is constantly increasing. And at a redshift of 2, when the universe was whatever it was, 1 + 2, 3 cubed, so 27 times more dense than it is now, this velocity scale became hot enough so that so I said that there were these two phases. If you heated gas only moderately, temperature would stabilize at something certainly below 10 to the 5th K, mostly below 10 to the 4 K. If you then really push it, heat it some more, it will suddenly switch into a temperature of well over 1 million degrees. So this transition, as the velocity scale increases, it gets to a critical point where it's able, the shocks associated with that velocity scale are able to drive the gas into this hot phase set by atomic physics. And now the potential wells associated with dark halos start to fill up with virial temperature gas, with gas in which the atoms are capable of moving, sustaining motion at the characteristic velocities also of the dark matter particles, so that they have a big, extensive, they genuinely fill the well. Before then, they were, until this breakthrough to a couple of million degrees and more, before then, they were collapsed to the bottom of the potential well, forming an object very much higher density than the overall, than the local dark matter density. And this very hot gas can't form stars. To form stars, this gas has to cool down. Okay, so now let's talk about simulations of galaxy formation. The beautiful thing about the standard cosmological model is that its parameters can all be set from studies of the cosmic microwave background. So we have precise information about the structure of the universe at a redshift of 1,000, which is so the photons which are were detected by that antenna in Holmdel in 1965 or whenever it was, had been streaming across the universe since a redshift of essentially 1,000. So they're conveying information about what was the structure of the universe at this extremely early time. I guess it was about 300,000 years old at the time, universe. So, and the physics involved, so we have the initial conditions and we understand the physics, which subsequently plays out. So yeah, you might think it was just straightforward, get hold of a supercomputer, solve the relevant equations that describe this physics, and bingo, you should be able to produce a simulation of the universe. Now, the problem is that the dynamic range upon which this physics plays out is way beyond our capacity. To get some sense of what's happening, nonlinear structures, so that those are structures which you have to compute numerically. Any structure which is merely a linear perturbation, you can do by pure thought. But once you get into the nonlinear regime, once the structures become large enough to be nonlinear, you can't do it by pure thought. So you better get your computer on the job. And they extend out to tens of megaparsecs. So in the present universe, you have to go to tens of megaparsecs, well, on the order of 10 megaparsecs, in order for the fluctuations to become more or less linear. Now, stars and active galactic nuclei release energy certainly on scales less than 1 parsec. So we need to simulate a volume which has tens of megaparsecs, say 10 megaparsecs inside, with cells which are only 1 parsec or better on the side. In other words, well, I've been generous here. I said we need 10 to the 18 resolution elements. You can do the arithmetic, it's really probably 10 to the 21. So that's just completely non-feasible and not that repeated anytime soon. But actually, the situation's worse than that, because most of the baryons in the universe, well, nearly all of them actually, are now invested in weakly collisional magnetized plasma, which is the kind of plasma that's of interest to people who want to do nuclear fusion. And they know, and we know, that we don't really understand. We do not understand the macrophysics of such matter, of weakly collisional plasmas. If we did, we would be, people would have already built fusion power stations, and we wouldn't be so worried about Mr. Putin's antics. So, and we do understand the physics of electrons and ions, magnetic fields and whatnot, about at the scale of an electron Lamore radius, which is sort of in a typical astrophysical plasma, might be sort of solar system scale. Basically, we simply don't have the computing power to compute the evolution. It's infuriating, but we know the initial conditions, we know the equations, but we're not able to compute the evolution. Nonetheless, people do compute. There's a huge industry doing this. These are actually just dark matter-only simulations. This is quite an ancient one, Schwingel et al. And I'm showing this because this is the kind of simulation which is absolutely credible. So this is okay because what they're doing is they've got a toy universe which contains only dark matter. They've got a large piece of the universe here. This is their simulation volume, and now they're showing you what you see as you zoom in on a particular small region. And this also makes the point that if you could see the dark matter, galaxies wouldn't seem isolated. So each of these things you imagine, this is a dark matter halo, it gets dressed with baryons, it has some stars, and these stars shine, but you see the dark matter picture doesn't look like the real galaxy picture. But when, so in the early attempts to simulate both to run simulations which included both ordinary matter and dark matter, what people did was assume that once gas became dense and cold, it turned itself into stars. And then the stars weren't a problem because the stars are essentially collisionless matter, so you could, get on computing. The result was, when you do this, if you assume that gas that becomes dense and cold turns itself into stars, then what you find is that most baryons are converted to stars in dwarf galaxies. So I said small things collapse first. The gas fell in, it became cold, it became dense, it turned into stars. And then when these dwarf galaxies merged with other dwarf galaxies to make larger galaxies, the stars just played along, rode along with the dark matter, and you got a universe in which the stars and the dark matter were behaving in a fairly similar way, but there were major objections. One is that, you end up with enormous numbers with a universe that's dominated by very luminous elliptical galaxies. That's say very luminous galaxies which don't have disks, don't have gas, and if you can occasionally find a disk somewhere, it's too small. So it's completely unlike the real universe. The fix is to put in strong feedback from massive stars. So I said there are these core collapse supernovae. They happen. Massive stars have short evolution times on the order of 10 mega years or so, which is nothing much on the time scales that we're discussing here, which are fractions of a gigayear. So what you think probably that did happen was that gas fell into some small gravitational potential well. The most dense and cold bits of it turned into stars. Those made some massive stars. Those massive stars evolved very quickly. Their cores collapsed to relativistic objects, blasting the rest of the star out into interstellar space, where it shock heated to 10 to the 7 Kelvin or whatever, to a really large temperature. The surrounding gas, this gas couldn't be contained by the feeble gravitational potential of this teeny-weeny galaxy, so it flowed out of the galaxy and stayed out for a long time whilst the dark matter, the dark matter halo, so this teeny-weeny galaxy merged with some other dark matter halo or a teeny galaxy to make a medium-sized galaxy with the gas all still out there, and eventually the gas comes back and falls in, and it's more of it turns into stars, and some more of it sent back out, etc., etc., etc. So what happens is you get two things. One is a big delay in the formation of stars. The gas is kept, the ordinary matter is kept in the gas phase for much longer. And two, you have gas kind of swilling around in the universe with velocities which are of hydrodynamical origin, not just gravitational origin. So these supernovae have driven shocks into the surrounding interstellar medium, which are pushed, mechanically pushed, using nuclear energy, the gas off in various directions. Right, and then you do much, much better. You put in enough feedback, and it needs to be a lot, and you get what you want. So this is a diagram which illustrates this from some simulations. So what we're plotting the efficiency, that's the fraction of the gas which turns into stars as a function of mass scale. And if you don't have any feedback, so what is this? 0.6. 0.6 of your material on the mass scale of our own galaxy, 10 to the 11 solar masses. Well, it's probably the halo mass. So that's probably a bit less than the mass of our own galaxy. But anyway, the point is that you get a very efficient conversion of matter into stars. That's what I was telling you about. And then if you put in various levels, more and more feedback, and it's just different feedback models, you drive this efficiency down, and then also people here are putting some AGN feedback. I'll talk about active galactic nuclear feedback a little bit later. So let's talk now about rich clusters of galaxies, because they provide very important information in this context. So when I was a graduate student, X-ray astronomy was really just opening up. There was it was far and away the most sexy topic in astronomy, I think, was then interacting binary stars, where one star dumps material on another star, making an X-ray source. But early X-ray observations discovered not only interacting binary stars, they also discovered that rich clusters of galaxies are X-ray emitters. And in the early days, it was widely thought that the source of these X-rays might be inverse Compton scattering, because the radio astronomers had discovered in the 1950s that that there were a lot of extremely relativistic electrons, electrons with gamma factors, you know, the gamma, the ratio of the energy to the rest mass energy of 10 to the 5 and more. So there were a lot of these relativistic, extremely relativistic electrons running around. Nobody really knew at that time where they came from. And if one of these electrons would collide with a microwave background photon, and the universe has an incredibly large number of microwave background photons, so having such a collision is a very likely thing, then the microwave background photon would be boosted to X-ray energies. So that's called the inverse Compton process. And this was very widely proposed, but the British satellite, the Ariel 5 satellite, showed that the X-rays are thermal. That is to say, they come from a plasma. It's just electrons scattering off ions. It's not relativistic electrons scattering off microwave background photons, because they could see this bump here. This is a spectrum from Ariel 5, the intensity of radiation this way, and energy in keV this way, and you can see there's a bump here, and this bump here is a spectrum, is a reflection of the fact that 24 and 25 times ionized iron clinging on to one or two electrons, and these one or two electrons make bound transitions with that kind of energy, and that established that it was a plasma. These clusters were X-ray sources because they were filled with gas at 10 to the 7 and 10 to the 8th degree Kelvin, which wasn't pure hydrogen and helium. It was polluted with oxygen, silicon, iron. These were all species for which soon people found the spectroscopic signatures. Okay. So these clusters are full of plasma. This plasma has a mass which is several times larger than the mass of the stars in the galaxies of the cluster. It's an enormous, it's the dominant reservoir of mass in clusters, and this plasma is not pristine at all. It has an abundance of iron, which is maybe a third of that of the sun. The heavy elements were presumably produced by the stars in the galaxies and then blasted by supernovae into the intergalactic medium. And this third, this abundance being about a third of the there's evidence also from our own galaxy. I must explain this a little bit every time. But there is evidence also in our own galaxy that an early generation of stars suddenly raised the iron abundance to maybe a third of the sun's iron abundance. So this is very clear evidence for feedback. This metal-rich, enormous quantity of metal-rich gas. Further evidence for feedback comes from groups of galaxies, so that's sort of lower mass clusters, because it turns out that the fraction of baryons, so from the microwave background, we think we know how much ordinary matter there is in the universe, what the density of ordinary matter is in the universe. the galaxies contain, stars in galaxies contain only a small fraction, fifth or something like that, of this, maybe even less than a fifth of this this hypothetical, right? But if you ask, and then in these clusters of galaxies, in these rich clusters of galaxies, you have about the canonical amount of baryons that are expected from cosmology, with only a fifth or something of the baryons of the stars, and the 4/5, or maybe it's a sixth in the stars, and 5/6 in the intergalactic medium. But in little groups of galaxies, as you go to smaller and smaller groups, which have lower and lower, less and less deep potential wells, what you find is that the proportion of the expected, from the microwave background, predicted amount of baryons that you see is falling. So that suggests that the reason it's falling is because in these weaker potential wells, we're not able to trap all of the supernova heated, etc., stuff. Moreover, the entropy of the gas in these groups is higher than the entropy you get if the gas had been heated to the observed temperature by gravitational infall. So again, it's a clear indication that entropy had been put into this gas by these exploding supernovae, etc. Non-gravitational heating. Right. So why are there so many? So rich clusters of galaxies contain very few galaxies like our own. The middles of rich clusters of galaxies are almost exclusively made up of elliptical galaxies and lenticular galaxies, which are galaxies like ours that don't have disks. I mean, don't have star-forming disks. Why is this? Well, it comes back to the origin, or one way to think about it is to think about the origin. Oh dear, time is running out. No, I think I won't explain this because time is running out. But basically, the idea is that the sun, material for which the sun is made, our piece of the disk, must have fallen into our galaxy from over 100 kiloparsecs away. And it's crashed down to, it's now in a much smaller volume, only 8 kiloparsecs from the center of the galaxy, because of this radiation of binding energy, etc., right? Okay. And in a cluster of galaxies, and it takes a certain amount of time, more than a gigayear, to fall from this kind of large radius into where the sun now is. So if you imagine in a cluster of galaxies, around each potential galaxy in early time, there will be this material that will be trying to fall down, and as it fell down, to spin up by the sort of process illustrated by skaters who pull in their spinning skaters who pull in their legs to spin themselves up by reducing their moment of inertia. As they're doing this, the whole cluster is collapsing, and the gas around each galaxy gets disturbed by the other galaxies falling towards this galaxy, etc., and the gas becomes common property. It all gets mixed together and heated up by this tumbling together of the galaxies, and that's why this gas is now and crucially heated up to this very high, to this above 1 million degrees Kelvin. So in fact, it's at 10 to the 7 and 10 to the 8 degrees Kelvin in these rich clusters, when it finds it very difficult to cool. Okay, so time is really up, but just a tiny bit about cooling flow issue. So you've got this huge body of gas. The density of this gas is, of course, in a cluster of galaxies, the density of gas is, of course, largest at the center of the cluster, where the gas has to bear the weight of all the overlying gas. And the cooling time gets shorter as the density gets higher. So then Curry and I, way back then, said, oh, well, probably what's happening is that the gas is flowing inwards and cooling, So with the sort of steady creeping of gas towards the center of the galaxy, the center of the cluster, but there were, it soon emerged, as better observational data appeared, that our model predicted that the X-ray brightness would rise towards the center too steeply. Moreover, the colors of the central galaxies in the cluster were inconsistent with stars forming out of this accreted gas. This led to almost a decade-long distraction due to these people in Cambridge, the so-called the theory of distributed mass dropout, which was that at various points as the gas approached the center, little overdensities would run away and become very overdense and form stars some way away from the middle of the cluster, but form not proper stars, but little weedy stars, which wouldn't create blue photons, the blue photons that you didn't see. Also, people saw H-alpha emitting filaments around the central galaxies of famous clusters, and these H-alpha emitting filaments were considered evidence of this dropout. But the dropout theory was bunkum, as some characters in Harvard showed in 1987. I mustn't explain the physics of this, but it's jolly good stuff. So what emerged, what became clear after two satellites started scanning the sky around 2000, year 2000, Chandra, which was an imaging instrument, and XMM Newton, which was the European counter-offering, which was a spectroscopic instrument, essentially, was that the plasma in these clusters is radiating, but it is not cooling. So these diagrams illustrate very beautifully this from Peterson's paper. The blue is the actual observed spectrum in three clusters. And the green is the spectrum that's predicted by the mass dropout theory. In the mass dropout theory, each parcel of gas transitions from the hot temperature, 10 to the 7 or whatever, down to nothing. And so it goes through all the various states of ionization, and it gets cool enough that things like oxygen and silicon, relatively low in the periodic, near the periodic table, form, and they contribute these spectral lines here, which are not seen. In order to get the red model, which gives a pretty decent account of the data, you have to say that there's an absolute flaw to the temperature distribution. There is gas at the main temperature, there is gas at maybe a third of the main temperature, and there is nothing cooler than that. So there cannot be this continuous cooling all the way down. Why is that? It's because, and graduate students and I predicted this back in 1990 something. It's because the black hole, the massive black hole in the center of these clusters, is an active galactic nucleus, i.e. it's an accreting black hole. The accreting black hole, by mechanisms that are not fully understood, fires jets. The jets, which are unsteady, jets come and go, and so it fires this thing out. This thing carves a channel and then impacts, shocks as it plows into the surrounding plasma, heating it. So in the middle here, so what basically happens is if the plasma in the middle cools too much, it feeds too much material to the accretion disk around the nuclear black hole. The nuclear black hole throws a fit, or is emboldened to spew out a powerful jet. It spews out its powerful jet, which heats and stirs, or both stirs and heats the surrounding plasma, and that restores order. And this is happening all the time. And here we are, you can even see it happening. This is a picture of the center of the Virgo cluster in radio continuum radiation. So this is radiation produced by those incredibly energetic electrons spiraling in a magnetic field. Here is a jet coming out, and here it is sort of externalizing itself to some extent on the. This is a backflow of magnetized plasma full of relativistic electrons. This obviously is due to the jet going the other way, which you can't see because of relativistic effects. And out here we have thermal plasma. You can actually see these objects at radio continuum frequencies heating the intergalactic medium. This is to explain how it is that stars form in galaxies like our own. So here we are. Here is the summary. I must stop. We do essentially understand star formation, galaxy formation, I think now. We have this initial Gaussian random fluctuation amplified and modified by gravity and by radiation pressure. Overdense regions collapse, virialize, and merge. Gas falls to the center of these things, create stars that explode, driving out most of the gas. Well, most of the gas, because even now, it's only a small fraction of all the baryons in the universe which are in stars. Most of the baryons out there in intergalactic, circumgalactic space at the very low temperature. Cosmic wave is constantly reforms on a larger scale. The velocity scale rises with the mass scale and the linear scale. And on each scale, gas falls in again and creates stars and is pushed out again. The ability to drive gas out diminishes with scale because the velocity scale is going up and the machines that do the driving are not improving, right? The machines that do the driving are the supernovae overwhelmingly, and they only have a certain amount of oomph. So eventually it ceases. So enriched clusters of galaxies is driving out has ceased. They are shut up, sealed boxes. After a redshift of 2, halos start to trap supernova heated gas. The velocity scale gets to the characteristic energy scales provided by supernovae. Central active galactic nuclei, central black holes, have a crucial role to play because they thermostat the pool of trapped gas. The pool of trapped gas would cool in the middle and cause a cooling catastrophe, as Carrie and I propose, if there weren't an AGN. But there is a black hole in the middle. It only has to eat a negligible amount of mass to produce a huge amount of energy. It does eat some cool gas, does a wobbly, reheats the pool of gas, and so keeps the pool of hot gas in a cluster essentially in statistical equilibrium, stasis. In disk galaxies, a fountain sustains star formation. This fountain doesn't work in a cluster of galaxies. I haven't explained that to you because the reasons are because in a cluster of galaxies are moving through the surrounding hot gas, and also the surrounding hot gas is very dense, which means that it's hostile to cold gas. It's likely to ablate and heat up cold gas, and as a result of this, star formation stops. In the technical jargon, star formation in these environments is quenched because galaxies run out of cold gas that they can turn into stars. And that's it. Thank you for your patience.
I think at some time for a few questions.
Apologies for the overrun.
I was wondering, of course, inflation also explains cause of Gaussian random field. You mentioned that you don't inflation. I was just wondering.
Well, yeah, it's straight physics, right? That we know that the vacuum has an enormous energy density, right? So the vacuum has an enormous energy density because the quantum fluctuations in the fields which are the substance of the vacuum. And you can do two things. One is you can just compute what is the energy density in the vacuum up to the kind of energy, it's an integral of decay again, up to the kind of wave numbers where we know the standard model, etc., is absolutely rock solid. What's done the LHC, etc. And that will give you a certain energy density. You can also You can also do the experimental thing with the Casimir effect, right? And you can empirically measure the energy density in the vacuum. And if you use either of these two numbers, I mean, it's a well-known fact, you conclude. Sorry, the other part of inflation is the absolutely correct statement that if the vacuum has non-negligible energy density, then through Einstein's equations, G mu nu equals T mu nu, the form of T mu nu by the Lorentz invariance has to be such that the vacuum is under tension, and tension creates this strong gravitational repulsion. Right? So if this definitely existing amount of T mu nu were put into those equations, the universe would be expanding with a cosmological constant, which is between 10 to the 18 and 10 to the 120 times larger than the actual. That's why there really is a cosmological constant, but the standard cosmology, right, includes cosmological constants and from type 1a supernovae. So what do you conclude from that? What you know from that for an absolute certainty is that Einstein's equations cannot be trusted at the level of quantum fluctuations, right? We don't know how to handle the vacuum fluctuations. I mean, so T mu nu is a classical object that you have to think of T mu nu as only the classical object in Einstein's equations, and you cannot extend it to be the expectation value, including quantum fluctuations. You know that's wrong. And what is the whole inflation drivel about? Various Platon fields and whatnot, where they calculate the vacuum energy and stuff it in there. I just don't see the point. It's completely absurd. We don't understand what happens at that level. And the honest thing is to say we don't understand, not to produce a lot of creativeness. Having said which, I do give talks about cosmology, including to schools, including inflation, etc., because I think it's a very beautiful creation. But it has as much scientific basis as what you will find in Genesis.
There's one on Zoom. James says, we are told that all massive galaxies have supermassive black holes at their center. What part do massive/supermassive black holes play in determining the scale of massive galaxies? Or which came first, supermassive black holes and massive galaxies?
Well, obviously, massive galaxies came first because the black holes are made. Okay. So even relatively minor galaxies like our own have black holes. We're not quite sure how many black holes there are in even smaller galaxies because technical difficulties in measuring the black hole, in detecting black holes. But what do we know about black holes? Well, we know that quasars are driven by black holes, and we know that the era of quasars, the number of ardently active. Zoltan presented a very lovely argument which enables you to predict what the masses are of the black holes at the middles of galaxies just by counting the amount of luminosity by all the quasars. Right? So you have some estimate of how much luminosity you get per solar mass which is stuck down a galactic center black hole. And you can see how many quasars and everything there are, even in 1980 something when Zoltan was doing this, it's possible, now it's super possible. And so you can say how many solar masses have been stuck down in a cubic, in a cubic megaparsec of the universe, how many solar masses have been stuck down to make galactic center black holes. And that number agrees remarkably well with the empirical number obtained by actually measuring black hole masses in individual galaxies. Okay, so what does that tell you? That tells you that the creation, the growth of black holes, the making of black holes is intimately related to the quasar luminosity density. And it's an empirical fact that the quasar luminosity density peaks in the same way that the luminosity from stars peaks, which what they call cosmic noons, a redshift of about 2. So these black holes formed on the same time plan as the majority of stars, and the majority of stars formed pretty much in their existing galaxies. That's a subtle point that probably seems a bit, but so black holes are co-equal with their galaxies essentially in their mass. Now, that doesn't say, of course, that that they weren't there in smaller galaxies which merged to make a bigger galaxy, and the black holes merged and all that. That's likely the case. But if you ask sort of where at that time they would have been lower mass to match their lower mass galaxies.